2D. Pin 12. What's on pin 13? Oh, no connect. Okay. So basically, this input and that output's not used. This is the most significant bit. He's used to feed the shift clock into the UART, and these two guys are probably unused because they don't need that frequency divider. So if I poke from there to there, I get ground, because that's what it is. And that guy's the most significant output. So since they picked the most significant bit, for half the count, they're only using 3 bits of the counter. So for half the count, they're going to be, 0 through 3, it's going to be low. And then for 4 through 7, right? Yeah, 4 through 7, it's going to be high. 1, 2, 4. Yep. So, yeah, these two chips here, their only purpose in life is to divide down the system clock coming from somewhere over here into, the system clock comes into this chip here and needs to be 30 times faster than the shift clock, which these two chips divide down. So both of those can go away. UART's gone. I'm never going to use it. It doesn't feed anything else. They're just taking up power. So back over here we go. And into solder mode. Okay, let's see if I can pop these chips out. There that one goes. So there is a standard counter, or a standard, well, semi-standard configurable up counter. And here is a slightly not quite unsoldered, but now it is, up down counter. I have used the up-down counters in projects before, and they're kind of useful. The preload portion of it is an interesting feature if you wanted to have, like a timer of some sort where you could set your time limit and then hit the start button. Up down is good for just general counting. So if you had, say, an assembly line with parts going across it, and you had a photo eye that would break every time a part went by, well, you could tie in the direction of the conveyor belt into the up-down pin, so as parts went by in one direction, it'd count down, say they're coming out of a bin. And then if the belt reversed and parts were going back in, it'd count back up. So, not a big thing. It's just kind of a neat part. Okay, so where are we at now? So we basically cleared out this whole section. I want to check out this 125, which is the other half of this 8-bit bus, because it's the only thing driven by this 138 3 to 8 decoder chip. So if there's nothing critical on him, I can pull both these chips out and clear off a couple more spots on the card. Okay. So what do we got here? So here we have 1, 2, and I bet 3 and 4 1, 2, 3, and 4 right there. Now I marked this pin. That meant he went someplace, and I already debugged who the hell he was. But I'm not sure what he was. Let's pull up the 125 logics and see what he's about. Now, the 125s on this card are being used as input gates. So basically there's some external I/O that's trying to get onto the bus to the processor. And this is the guy letting it do it. So why is the outputs A's are the inputs? So it's every 3 starting from that end. Okay, every 3. So this is the bus, and that is an input. Now this is where it's going to start to suck. Can't really tell. There's so much stuff crammed on here. Oh, I lucked out. So this guy's input's coming on the back of the card. It's coming to that bump right there, which then goes to this bump right here and heads off across the card. Gotta love it. So it's 1 in from the edge. Okay, pull up resistor or pull down, one of the two. Pull up resistor, and then it goes around the corner. 1, 2, 3, 1, 2, 3. I think it goes. Product goes under that connector. I'm going to pop that keyboard connector off real quick, just so I can finish tracing that connection. You know, it goes right under this connector, and it's just too big of a pain in the butt to see, as is. Eventually the connector has to come off anyways, and it's just a connector, so if I need to figure out what was where, it's pretty straightforward. And let's see if I got all the solder out or not. Now, this connector is kind of glued on. Oh, look at that. Isn't that nice? Okay, that'll make tracing that net a lot easier. So the net, I think, comes in. It was pin 2 on here, and I think it's one of these two. That pin right there. Which then comes into that connector. Okay, so this pin's a don't care. He went to the keyboard. So he's part of the keyboard multiplex, demultiplex logic somehow. In fact, I don't have a keyboard, never will have a keyboard. He can just get punted. This pin right here, which is 1, 2, 3 over. 1, 2, 3 over. Why do I have him marked off? Oh, because he goes there. Ah, he was the pain in the keister pin. That's right, he came from somewheres over here. He might have been the pen input pin. No, he came off. Yep. So the pen input here went to the last JK flip-flop, or SR flip-flop, and then came back into this guy. So that's why he's marked off. So here's the output, here's another input. So 1, 2, 3 over. 1, 2, 3. Well, this one goes multiple spots. Goes here and goes there. And the same thing with the end, the last one. He comes from multiple spots. He goes to these two pads right here. Which they go right to there. Which they go right to there. Hey, one of these looks to be the button input. So, let's take... Which one does not go multiple spots? Upper 2. Let's see where he goes. Right next to the button. Boy, they're just sort of trucking all the way. Oh, I think it goes to this connector. Yep, another input pin from this missing dip socket. This guy goes multiple places, but I think one of the places he goes is right there. So that's the button input. Now where does the other side go? I'm pretty sure there was a second side to him. He went right there. Right there, I bet. Three in along this top edge. Okay, he gets... that button plus 3 in. 2 in, 3 in. 2 in, 3 in. He's got a pull up, flips around there, flips around those two bumps, and I think it goes to right there. Yep. So this is more button input stuff. Now the interesting thing is that pulled? Huh. Somewhere along the way here, this ground got separated from this ground. And I'm guessing it's this hole. This is kind of a, not a design flaw, but you know, you want to avoid this when designing cards. In this case, they have a mounting hole which you put a screw through, acting as the conducting, as a carrying via to connect this trace to the trace on the back side. One of the problems with doing that is if the screw abrades the sides of the hole, it can actually open that connection up. A better way to have done this would have been to just run this trace over and pop a via right next to it to connect these two pieces while still connecting to this pad. So you can still use this as a frame ground, but don't rely on it to get power from one side to the other on the raw card. But anyways, what I just learned is this switch is tied to ground, and it's part of this keypad input mux. So somehow is smart enough that when you push this button down and short the works out, it can tell the difference between this button and pressing buttons on this keypad. But either way, he can go away. He's part of this keypad key press circuit, and I don't have that keyboard. I don't really want to use this button for anything, so it can all just go away. Since he can go away, he can go away as well. And I think that's the end of this corner here. Next thing up on my list to finish is I want to go through what's left on this keypad input, because I'm betting a few of the chips over here can go away. And then to start digging into the driving logic between all these chips, the micro, the flash, and the RAM, or the ROM and the RAM, and the various timing and P-good circuit, reset circuit. But I may finish up taking off the unnecessary circuitry, so these two, this, and whatever's just for this keypad, and then leave the debug of the rest of the stuff, or reverse engineering of the rest of the stuff, until another day, because it's getting kind of late here.